For this ketone, we call it butanone. Now you should observe that there should be 3 signals, 3 different kinds of protons, and for this signal here, the one in red, it should be a singlet. Why singlet? The neighboring proton is 0, so 0 plus 1 is 1. Why 0? Let's check. This carbon here, where this proton connects to the first carbon, and this carbon has 0 protons, so definitely singlet. When you see an ethyl group, always tell yourself that ethyl gives rise to a triplet and quartet, and you should know why I explained to you just now. So the one that is a quartet must belong to the CH2. The one that's triplet must be your CH3. It makes sense that the CH2 peak is of a higher chemical shift, downfield, low field, compared to the other one, the CH3, because CH2 is closer to the electron withdrawing CO double bond. It deshields it. Next, ethyl acetate. Take note, this is an ester. So again, we should see 1, 2, 3, 3 different kinds of proton environment. So 1, 2, 3, singlet for the one there's no coupling here, 0 neighboring proton, ethyl group, quartet, triplet. If you measure the integration, you get 2:3:3. It measures exactly well. Next, another ester, we have ethyl propanoate. We should see 1, 2, 3, 4 kinds of proton, and the ratio should be 3:2:3. And indeed, you see here, 3, 3, 1.99 take it as 2, 1.99 take it as 2, so 2, 2, 3, 3. Perfect. And we can assign them. So you might ask, the 2, okay, I've got 2 protons that has an integration of 2, but which one is it? So you can refer to the table that's given to you, or you can use some prediction. Think about it. This CH2 here, that my cursor is hovering to, is closer to the oxygen. It's directly connected to electronegative oxygen, so definitely it's very deshielded. It will be more downfield compared to the other CH2 in red. Now in 1 propanol or propan-1-nol, I will see 3:2:2:1 ratio. 3, 2, 2, 1. And indeed we see 3, 2, 2, 1. Ta-da! Beautiful, isn't it? It's simple. It's like solving puzzle. It's so exciting. Now same thing goes. Which of the CH2 belongs to this signal? You know. I told you, because this CH2 in black is closer to the electron withdrawing electronegative oxygen, so definitely going to be more downfield. Another example here, your acetophenone. So now you got your benzene ring. Now we count all these 5, although they are not really the same, right? These 2 are the same because you see a line of symmetry here. These 2 are the same, those 2 are the same. This is unique on its own, but since all of them, all 5, are connected to a benzene ring, for your syllabus, your case, you can take it as a whole entity. Okay? But when we zoom down, go deep down to the core, they are different. So you see here, the 2 that are blue, I was saying just now, they come in a pair. The one that are in red is a pair, and the one that's a pink is alone. So if you go down to high resolution, you should see a 2:2:1 ratio, and indeed we do see that 2:2:1. For the position of these 5 protons, we do not have to know why are the one blue color has a high chemical shift. Not in your syllabus, but you can ask me, I will tell you why. Okay, so that's all for this topic. Remember the 4 things you need to remember for NMR spectroscopy, how to solve an unknown NMR spectral, and to take a look at a given molecule, given chemical formula, predict the splitting pattern, the number of protons, the chemical shift relative to each other. These are the things you have to learn and know for this topic. Splitting, integration, chemical shift, and the number of signals. So thank you. I'll see you soon. Bye bye.